Oh, it's okay. All right. Okay, so we bring the variable to one side, all the variables to one side, and next we factor. So how am I going to factor this? Some big numbers here, okay? So when we have big numbers, inspection works a lot better than decomposition. Okay, so we're going to do multiples. One-on-one. Whenever I do inspection, I always try and start, I don't know if it's just my luck or just the odds are, if you try and start in the middle of the multiples, okay, it just tends to work. I don't know, that's just my experience. I've done a lot of factoring. So I'm going to start with 60 and 30, and I'm pretty sure that those are actually the numbers, but just in generally speaking, I try to start in the middle. So if it's like, say for example, 36, there's a bunch of ways to get 36, right? 18 times 2, 9 times 4, 6 times 6. I would always start in the middle, 6 times 6. Okay, it just kind of works. All right, so now can I use the multiple of 60 and 30 to make 30? Yeah, I can, right? So I need to have, they're both, sorry, in this case, they're both going to be the same sign. They're both going to be negative. So I can't actually use it, right? I can't make 30 and 60 into 30 with both of them being negative. So those are not the right numbers. So we need to try a different number. Sorry?
It's supposed to be negative 1800.
Ah, that would make sense. Yeah, okay. So now it works. So 60 and 30, and then you minus them. So 60 has to be negative. So we're going to put L here, L here, 60 and 30. 60 is negative because our middle term is negative. The bigger one is negative and positive 30. Okay? So then from that, we get two values for the length. One is the length equals negative 30, or length equals 60. Okay? Can this work? No, because we're not in the 13th dimension. We don't know. We don't have negative lengths in this world. Okay, so that doesn't work. All right. So we know then our length is 60 meters. Well, we know if our length is 60 meters, we can plug that back into here and figure out our width. Okay, so those are the dimensions of our skating rink. Sorry. Any questions? So, probably the hardest thing was the factoring in this question. Yeah.
Was it just coincidence that 30 was the number that you factored?
Yes. Yeah, it was coincidence. Yeah. All right, so here you see the books, the textbook solution. They go through the same steps. They find the length is 60 and the width is 30. Okay? Always a great idea if you don't understand something to actually read through the textbook. They explain stuff in more depth than I do. Okay? See how they're explaining each step. Okay? So this is actually one of the better textbooks. I don't have any like serious complaints about this textbook. So it's a great textbook to use. So the next method they use is a numerical model. You can see they start guessing here and checking. I don't like that. Okay? So I won't ask you to do that. Okay, they end up having to use a table of values to figure this out, which again is not ideal. And finally, the last method is, again, becoming archaic, right? This really old graphing calculator, which we don't use. We're going to try and see if we can use our phones. There's an app now that actually is that old school graphing calculator. Okay, it's just called the TI, whatever, 864. All right, so there's that. That's all example 1, okay? We can answer some of these reflecting questions. Would the function change if width was used as the independent variable instead of the length? So it's referring to the graph here. So remember, when we talk about independent versus dependent, independent is always on the x-axis, and dependent is always on the y. And so it's asking, how would the function change? Would it look different if we switch these two? Yeah, of course, right? It would be the inverse. Okay? Is it necessary to restrict the domain and range in this problem? What do you guys think? Is it necessary to restrict that? The domain being either the length or the width. Would you want to have any values out over here?
No.
No, it'd have to be greater, right? Because there's no such thing as a negative dimension or negative length. Okay, so yeah, you would want to restrict it. Okay. It would have to also not be down here, right? So you'd only have this quadrant active on this particular function. Okay, that's because you can't have a negative width and you can't have a negative length. So all of these quadrants are undefined. Why was it useful to think of the relationship between the length and the width as a function to solve the problem? Because it allowed us to create an equation that we could then factor and solve. All right, example 2, using reasoning to decide whether a relation is a function. So one of the main reasons why I did want to go to this method of having the camera is just the amount of time it's going to take me to draw some of these graphs. They get absolutely ridiculous later on in these chapters, and it actually takes me 10 to 20 minutes to draw the graph accurately. With this, we're going to save all that time, okay, because the book does them beautifully. Okay, so we can just use these. So it says decide whether each function relation is a function, state the domain and range. So what's the thing we can use for A to check if it's a function, Luke?
Vertical line test.
Yeah, so we're going to go ahead and use the vertical line test here. Vertical line test. Okay, so we do that by just drawing a completely straight vertical line wherever we want across the graph. Okay, and you're just checking to see that it only touches the function at one point. Okay, so is this a function?
Yes.
Yes. Okay, next one, 1 over x squared. Is this a function?
Yeah,
How do we know, Luigi?
because you could kind of picture the function in your head, and you could also apply the vertical line test.
Okay, so we know the parent function looks like this, right? That's y equals 1 over x. Okay, so x squared is just going to be steeper lines. The vertical line test is still going to work. Okay, so this is it's definitely a function. Any equation that you can see that comes from a parent function that's very easily discernible from the parent function obviously is a function. Okay, and the last one. So this is just set points. These are the x coordinates. And these are the y coordinates. So I'll tell you how we know if it's a function or not, or if it's just a relation. If every x coordinate has a unique value of y, you can't have, when you have them lined up like this, you can have what we call convergence, but you can't have separatism or moving away from each other. So starting from the left-hand side to the right-hand side, if lines converge, it's fine. If lines divert, so if you had this is like a kind of a shortcut to tell. If you had anything that looked like this, anything that looked like that, where you have diverging lines, see how these diverge here? And these converge over here? So convergence is okay, because each x coordinate, although it's not unique, has a unique y value. Okay, so that's what's important. Any questions with that?
So C is a function?
Yes, it's a function, yes. So function, because another way to say it is only one output. Okay, so there's only one value for each value of x. In this scenario here, for 2, there's a value of 5 for y, and there's a value of 2 for y, for the same value of x. So this is not a function. I'm trying to reiterate, not a function because 2 y values for the same x value. Okay? You can have two x values that are the same, or sorry, two y values that are the same, but they have to be different x values. Okay, so I'll draw that up here. If we have the sine graph, this we all know is a function, of course. This is y equals 1, this is y equals 1. Okay, you can have two values of y equals 1, but they have to be unique x values. X value needs to be unique. Any questions about that? No? Okay, let's move on. Thanks. Hope it wasn't the video camera. Hope it wasn't the video camera. No, just me. Okay. Here's the solutions. The first one, we did use the vertical line test. Okay, it worked. Oh, one of the things we didn't do was domain and range. Okay, so we're going to do it here. Domain are all the possible x values. We see that this arrow goes off. Okay, even though it's going up a lot quicker than it is going to the right, it still ends up covering all the x values. Okay, so the domain, and the domain goes this way, there's a big arrow here. So we know it covers all of the x values, so that's why the domain is XER. Okay, the range is all of the y values. So we can see, because this line bottoms out, so to speak, at -2, it doesn't go below -2. So the y values are all real y values that are greater than -2. Any questions with the domain and range here? All right, next one. It's coordinates. They're using a table here, a table of values, and they're figuring out, they're subbing in values to see that there's a unique value of y for each value of x. Okay, so they figure out it's a function. So function. The domain, again, they're using that parent function to determine the domain, which they have a vertical asymptote defined at x equals 0, so that's this. It has a horizontal asymptote defined by the equation y equals 0, okay, and that's right from the parent function. That looks like that, okay, and we went over that yesterday. There's a horizontal asymptote here at y equals 0, and there's a vertical asymptote there at x equals 0. Any questions about that one? Domain and range, yeah.
Shouldn't it be cannot equal, not greater than 0 for y? Cannot. 'Cause it's an
Yeah.
asymptote.
No, because this is squared here. Any negative value will also be positive. So that doesn't exist, right? Any negative value you plug into 1 over x squared is going to be positive. So there's no negative values for any value of x. So it actually look like that. Luigi?
So wouldn't it be greater than 0 for x, because there's no negative value?
Yeah.
The x values, they're all negative. It goes this way.
It just can't equal 0. You can because the 0 point
Oh,
is the
okay,
asymptote.
yeah.
The square flips this.
Yeah.
Okay? So any negative value of x you plug in is actually going to be a positive value. Right? So let me draw that one more time. Okay, and if you want to see if this is correct, we can plug in some numbers. So let's say x is 1, y is going to be 1, x is -1, y is going to be 1, x is 2. So we plug in x equals 2, so you get 1/4. So y would be 1/4, which is over here. You plug in x equals -2, you would get 1/4. Okay, so they're exact mirrors. All right? Finally, that last one is a function as well. It says the mapping diagram indicates that each number in the domain corresponds to only one number in the range. A function can have converging arrows but cannot diverging arrows. Right there. Okay, that's what I was talking about. Converging versus diverging. This is converging. Okay? No questions? Moving on. I believe this is the last example in section 1.1. So we got the infamous Ferris wheel. We'll be doing a lot of stuff. If you haven't already been sick of them in grade 11, you will be sick of them by the end of grade 12. A lot of stuff with Ferris wheels. Okay? And the reason for that is because they mimic a sinusoidal or trigonometric function. Okay? So they kind of mimic that up and down motion. Right? Luke, can you read this?
Top part.
Yep. No.
Niall rides a Ferris wheel that has a diameter of 6 meters. Let me just take it out. Okay. Nail rides a Ferris wheel that has a diameter of 6 meters. The axle of the Ferris wheel is 4 meters above the ground. The Ferris wheel takes 90 seconds to make one complete rotation, and Nail rides for 10 rotations. What are the domain and range of the function that models Nail's height above the ground in terms of time while he rides the Ferris wheel?
Okay, good. So it's important to understand what these equations are, right? So let's talk a little bit about them before we try and answer this. Kevin, can you tell us what that A does? So all of these equations are variations on the parent function y equals sine x or y equals cos x, which looks like that. Okay, that's what these two functions are. I have some space, I'm going to draw it over here. So y equals sine x. Okay, and of course we know this is 1, negative 1, 360. Okay, Kevin, well, hi Marco. What's this A do right here, this guy?
It determines the amplitude.
Right, good. So the amplitude being the height of these humps, so to speak. So the A value here determines how high these humps are going to go. Okay? What does the K value determine? Yeah. Sorry. Yes, very good. K determines the horizontal compression. So how many cycles this is going to go through before it gets to 360 or whatever time we're looking at. Okay, good. David, what's the D tell us?
The horizontal translation.
Yeah, good. The horizontal translation, the horizontal shift. Okay, so it's going to tell us which way this graph moves, left or right. Okay, and the C value. Yeah, Lyndon? Sorry? Yeah, vertical translation. So let's just put that in here. So this is our vertical translation. This is our horizontal translation. This is our horizontal compression or stretch. And then this is our amplitude or height. Let's put height of humps. Okay, so that's all good information to have. Typically we choose the sinusoidal function if we're entering kind of in the middle. Okay, that's because the height is in the middle. So if we want to track something from the middle, we'll use sinusoidal. If we want to track something from the top, let's say we enter the Ferris wheel at the top, so time 0 is at the top, we would use cos x. But they're the same functions, right? They're just translations of each other. They're just horizontal translations of each other. Okay? So a lot of the times in this course, I'm not going to care whether you answer the question using cos or sine. As long as you make the correct adjustments to the value of D, you could both be right. Okay? If I give you a graph and it looks like this, somebody might say that that's y equals sine x. Someone else might say, no, that's y equals cos x minus 90. Okay? Which is the same thing. All right? Okay, so it tells us that the Ferris wheel has a diameter of 6 meters. So there's a beautiful drawing here of a nice Ferris wheel. I could never do that on the board, never. Here's the diameter. So it even breaks this out for us here. We have 3 meters to the center and 3 meters to the center. So there's our diameter of 6 meters, which comes right from the problem. The axle of the Ferris wheel is, I wrote on it, but it's 4 meters above the ground. Okay, so that's where this height comes in. 4 meters here. Okay? And you can see it nice, neatly labeled over here. The Ferris wheel takes 90 seconds to make 1 complete rotation, and Nail rides for 10 rotations. So if he's riding for 10 rotations, our graph is going to be like this 10 times, right? Because he's going up and down 10 times. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's our graph, believe it or not. Okay? And it's not drawn very well. It would be even worse on the blackboard. Sure, sorry. Thanks. Yeah, not very good. Okay. You get the point, right? You get the point? Good. All right. So what's here? What's all the way here? How long has it been at this point?
90 times 10.
Good. 90, because it takes 90 seconds for one round, so we have 900 seconds here. Okay, so that's the total length of time that he's on it. So first it says, what are the domain? Actually, let's fill in a few more things. Okay, the middle of the Ferris wheel, we can see here, we've already determined, it tells us is actually 4 meters off the ground. So this then, this would be 4 here, 4 meters, and our 0, 0 is down here. Okay, so here's 0, 0. And this, the bottom of the Ferris wheel here, is 1 meter off the ground. Any questions there?
I thought it was 4 meters. Oh no,
The center is 4 meters, so we're going up and down around the center. But the Ferris wheel comes all the way down. See right here? It comes down to 1 meter off the ground.
So the top is 7, right?
Yes.
Yeah.
Yep, exactly. The top is 7. Okay, because we're going down 3, so we're going up 3. Okay, any questions there?
Sir, doesn't he get in at 1 meter though?
Does it tell us he gets in at 1, or does it not even matter? It tells us? It doesn't matter, right? He's still going to ride it for 90 seconds. You're right, this whole thing could be shifted over where it actually starts down here, right? Yeah. Let's just say he had a helicopter and he entered at the exact center. I don't think it matters for the question, but good thing to point out. Terry?
It has to spin, and let's just say he stops in the middle.
Yeah, no, it's a good point though. Like if you wanted to start the graph at time equals 0, if this time equals 0, the way I've drawn it, I'm saying that he's actually getting in the Ferris wheel up here, which is not really, it's not correct. You would actually, I'm not going to draw it again with all the squigglies, but this would be down here. So this whole thing would shift over. Okay? All right, so there would be a horizontal shift going on. All right? Okay, what are the domain and range of the function that models Nail's height above the ground in terms of time which he rides the Ferris wheel? So domain, this is probably the easier one, right? Domain, because it's a solid line, right away I know. Just because it's a solid line, I know what? Nicholas, for domain. What am I going to write? It's a solid line, I have to write something at the beginning of the domain. Equals what? Good. XER, elements of the real. Good. And I write that, why? Because solid line. Okay? That's why we write that. Some people just like, oh, I don't know, I write that because we always write it. That's telling us that it's including all of these values in between. Okay, now we're going to give it a range. What's the range going to be? See somebody else. Alex. What's the domain?
Can't go past 900 seconds.
Yeah, so how would you say that?
Well, x is less than 900.
Okay. What else? You're missing something.
Or t equal to 900 as well.
Well, unless you have a time machine, you're going to put on another side of that range, right? For time? What's it going to be?
Okay, 0.
Yeah, it's got to be greater than 0, right? Time can't be negative, right? So because time is our x value, we need to put 0 as the border, okay? And the way I've taught students in the past in grade 11 this, how to do domain, is if you set it up where you put x in the middle, you can kind of read it from left to right, the points, so from 0 to 90. So sometimes I'll tell my students for domain, if it's a solid line, you write xer, okay? And then put x in the middle and put these greater than signs the same direction, and then start on the left. So you can almost set that up at the beginning. Okay, now for any line that I draw, this is -5, this is +7. I set that up already for domain. Now I just go I read it from left to right. -5 and +7. People get confused with which way to put these arrows. Okay? If I had something like this, let's just say domain, and let's say I just set it up the same way. Mr. Mills taught me set it up like this so I don't get confused with the greater than signs. Okay? And now I go to look at this graph. Okay, which we all know is y equals x squared. My left-hand side boundary for x, it doesn't exist. Okay, so I could put infinity, or sorry, negative infinity. Okay, and it goes all the way to infinity, so I could put positive infinity. This is the same thing as this, right? Because I'm saying all real numbers. Okay, an example with one border now. I'll do one more, okay? Because people mess up domain all the time. It's a really simple concept. So I'm doing domain for this graph now.
So we put restrictions also on the one?
Yeah, I'm just doing domain. I'm just showing it. You would do the same thing. Domain, range is the same thing. You just start from the bottom and go up. So last one here. I'm going to write it out. And I tell my grade 11 guys, write it like this. It's a solid line. You know that part's true. Okay? You're going to put x in the middle. You're going to put the greater than signs the same way. Now you're going to go back and look at the graph. You're going to read it from left to right. So what's the border? What's the limit of the left-hand side? 0. I'm going to put 0. What's the limit of the right-hand side? Infinity, which is nothing. So that would be the answer. So 0, x is greater than and less than 0. Greater than or equal. Okay? Range, you do the same thing. So write it out the same way. Okay, now you just read from the bottom to the top. What's the bottom? 0. And what's the top? Infinity, so this is gone. That's it. Okay? If you have a better understanding of these symbols, greater than and less than, you can write it any way you want. You could write it like this, right, if you wanted to. Same thing. But if you have trouble mixing these up, it's going to be wrong on a test, right? So if you write this out and then just follow those rules, you can do it. Okay?
So can I see the bottom of that sheet?
Yeah, I'll give it to you in a second. All right, so summary very quickly here. These things, if you guys miss a class, if you're trying to study on your own, if you forget everything and you're looking to review for an exam, these are beautiful sheets, these summaries. They sum up everything very nicely in one page. Okay, so I very much encourage everybody to use these summaries. So we'll read through it. Alan.
Okay, so key ideas. A function is a relation in which there is a unique output for each input. This means that each value of the independent variable, the domain, must correspond to one and only one value of the dependent variable, the range. Functions can be represented graphically, numerically, or algebraically.
Okay, and there's our examples graphically. We know this passes all my vertical line test, only one spot. numerically, so you'll get ordered pairs. This, you can have a function that's described like this, right? These first values are your x, the second values are your y. Okay, table of values or a mapping diagram. You need to understand these, okay? These will be on the quiz. You need to understand what's going on here. These are the x values and these are the y. So if I said graph this, you should know how to graph it. Okay?
So
Yeah.
you take any form of how we
Yes.
order those?
That's right. Yeah, these three forms, yeah. Okay? Algebraic models, my favorite. Look like that. Seen them all before. There's also all types, right? Okay, and all variations of those. Yeah, Joseph.
Can we go back to our step in the algebraic data solving?
Which example?
On the very first one. Yeah.
Okay. Yep.
We went from, we got 180 equals L times W, and that led to W equals 180 over L. Where did we get L equals 180 over L? Sorry, 1800 over L.
Yeah, so see this arrow here? I'm taking this value for W, 1800 over L, and I'm plugging it in for W.
Okay, okay.
Okay?
Yeah.
Maybe if you want to go back to the first one, just we'll finish the summary and then I'll go back, okay, at the very end. All right, function notation. F at x is used to represent values of the independent variable in a function. So y equals f at x. Why do this? Why do we do this? Why? Why not just call it y? Why do we change it to f at x? To confuse everybody? Yeah, Lyndon.
Determine the variable when by a certain number is at x.
Yes, very good, because it gives us an idea of both values, the y value and the x value. It's telling you, so for instance, you can write f at 5. Okay, so it's giving you what's the y value when the x value is 5. Okay, that's one good way. Why else would we use this? Why else is it a good idea? How about when we're doing a speed time graph or distance time graph? Why do you think it's better to have this as opposed to this for both? Yeah.
It eliminates the time that you have to take note of graphing the whole thing. Why you can just graph that single point?
No. It's more just like it's more just for information, right? We know we're dealing with speed here. We can't call everything y, right? It's going to get confusing, especially if we start graphing things where there's 2 or 3 functions on a graph, right? There's a function here, there's a function over here. If I call this y and I call this y, I'm going to start to get really confused. Okay, so we end up calling this f at x, and we end up calling this g at x. Okay, so that's another reason. Why we use s and d? Well, when we're doing science graphs, we want to know what that variable is. Oh, it's speed. I want to call everything y. So there's advantages, okay? There's 1 advantage, 2 advantage, 3 different advantages on why we use function notation. You can use the vertical line test. We know all about that. The domain and range of a function depend on the type of function, obviously. The domain and range of a function that models a particular situation may need to be restricted based on the situation. Example, negative values for length or time. Any other questions? All right.